Hello, everyone. We are Final Project Group 8, and today we're presenting VIVIRE, an emergency room triage prioritization score system. My name is Morgan Moat, and I'm joined by Israel Akbati and Aaron Martin, and our project addresses a critical problem in emergency medicine, which is how to consistently and quickly prioritize patient care under pressure. So VIVIRE is a clinical decision support system that computes a real-time triage priority score from 1 to 100 based on patient vitals. The goal is not to replace clinicians, but to provide a more structured and data-driven reference point that improves consistency in triage decisions. So the key capabilities of this system include a secure authentication with role-based access control, a secured triage intake interface, a deterministic real-time scoring engine, severity classification, and full audit logging for traceability. The operational workflow is pretty straightforward. A triage nurse inputs patient vitals, the system computes a severity score, and then the clinician uses that score to prioritize care. And this helps create a consistent and repeatable triage process in high-pressure environments. So the project motivation, essentially, we know that emergency rooms today are often overcrowded and resource constrained. And in these environments, prioritization errors can directly impact patient outcomes, where delays or inconsistencies in triage can lead to worsening conditions, missed critical cases, or preventable complications. So this system is motivated by the need to introduce structure, speed, and consistency into that decision-making process. So this is our first architecture option, which is a layered monolithic architecture. And this system is organized into 5 layers: presentation, application API, domain logic, data access, and the database. All components operate within a single system boundary, which simplifies deployment and debugging, and data flows top down. So user input down to validation, down to scoring, down to persistence, and finally output. For the layered class diagram, this shows how the system is implemented at the class level. So we can see that core entities include user, vital record, alert, audit log, and service classes such as scoring service, auth service, and alert service, which handle business logic. And these classes directly correspond to responsibilities defined in each architectural layer. So here we can see that the layered mapping shows how the architecture maps to implementation. So for example, the presentation layer is implemented using a React front end. The API layer uses fast API routes. The domain logic layer includes services like scoring service. The data access layer uses SQL Alchemy ORM, and the database layer is implemented using SQLite. And this demonstrates a direct and traceable connection between design and code. And here we can see all of the components and their corresponding implementations. So for our second architecture, we selected a microservices-based design, and here the system is decomposed into independent services. We have the API gateway, the authentication service, the scoring service, audit logging service, and record retrieval service, where each service is independently deployable and communicates via REST APIs. Each service is also stateless, and services have their own databases, and only that service can directly access the data in the database. And then each service is loosely coupled to others, so some parts of the system can still fail without affecting other parts, like record retrieval could fail, and users could still submit new assessments. And then for our microservices class diagram, we can see that in this architecture, each service owns its own data and logic. So for example, the scoring service contains scoring logic, the auth service manages users and tokens, and the audit service handles logging and records. And this separation improves modularity and scalability. And furthermore, the gateway allows external access to auth service, scoring service, and record retrieval service, where the audit service is not exposed by the gateway because it is not public facing. And the mapping shows how each component corresponds to an independent code base. So for example, gateway corresponds to gateway or the main Python script. The auth corresponds to the auth service. Scoring corresponds to scoring service, and audit corresponds to audit service. And this architecture essentially enables independent deployment and scaling of each service. And this table summarizes the key trade-offs. And for the layered architecture, we can see that it offers lower complexity, easier deployment, and limited scalability as one of the holdbacks. And for microservices, we can see higher complexity with greater scalability and stronger fault isolation. So the trade-off is essentially simplicity versus scalability. And the key distinction here is that layered architecture is optimized for simplicity and ease of development, while microservices is optimized for scalability, fault isolation, and long-term system evolution.
Thanks, Morgan. I'm Aaron Martin. I'm going to talk about the rationale, like why we chose one service over the other. These next couple of slides are pretty dense, so I'm going to give you a high-level review of them, and we'll get going. Okay, so because the VIVIRE system is used in an emergency room, availability and performance are important because situations might be emergencies. Security is also an important concern because we're dealing with medical records. The microservice system addresses availability through better fault tolerance and better fault isolation. It also provides for faster recovery from faults. It addresses performance by supporting independent scaling. It addresses security by having each service validate authentication and by using separate databases. So access to one service doesn't get you access to another service or its data. This rationale evolved from our ATAM risk assessment that we did on both systems, and we'll talk about those in the next slides. So now we're talking about the layered system. We use the architectural trade-off analysis method. We had 6 different scenarios. So the first scenario that we considered for both systems is a submission of an assessment under normal conditions. The second was scoring with a database failure. The third was an unauthorized attempt to access data. The next was retrieval of assessments under normal conditions. The next is high load conditions, and finally, change to the scoring system. So when we talk about the layered system here, we're going to just sort of summarize our findings. The layered system has a single point of failure, limited scalability, and components are tightly coupled. It would be suitable for a small scale deployment, but it is less suitable for what we envision for the VIVIRE system. And now we're going to go through each of the 6 scenarios for this system. So this scenario was the availability, was normal submission of an assessment. Because although Logic shares one database and one execution environment, any slowdown in audit logging or resource usage cascades through the entire monolith and directly increases scoring latency. The next scenario was a failure during the database. Because the monolith relies on a single database as a single deployable unit, any database failure brings down the entire system and requires a full restart. The next scenario is that unauthorized attempt at data access. So the centralized checks for security are simple, but shared code and logging overhead means a single flaw or slowdown can impact multiple parts of the system. if you can get by that one central security check, then you're into the system, which is not great. The next scenario is the retrieval of assessments by the admin under normal conditions. Because all features share one single database, queries slow down from contention even through in-process calls remain, even though in-process calls remain fast. However, the centralized schema stays consistent. The fifth scenario is a high load scenario, so 50 concurrent users. Because the monolith can't scale parts independently, shared database and CPU contention slows the system under load, and fast in-process calls can't overcome the structural limitations. And then the final scenario here is basically a change to the scoring algorithm. A single code base is tightly coupled layers make changes risky because updates can ripple across the system. And now, so you saw back here, you saw all these tables that show the architectural decisions. Here is the grid that shows what those codes mean. We'll keep on going. Again, these are pretty dense, so we're going to go by quickly. The microservice system distributes complexity across multiple services. This is greater operational overhead from deployment, monitoring, and networking. There is a potential increased latency from inter-service REST calls. Despite being operationally complex, the microsystems provide a resilient, scalable foundation for a production-grade system. So then we're going to talk about those same 6 scenarios. This first one is a normal submission of assessment under normal conditions. Synchronous logging and single host deployment adds latency and availability risk, while stateless services separate database and downstream Java token checks, improve reliability and security at some performance cost. The next scenario is a database failure of the audit system database during scoring. Because scoring depends on a single unreplicated audit database, any audit DB failure stops scoring until the whole system recovers. But stateless scoring makes the restart easier. In this particular scenario shows the strength of the ATAM process for us anyway. It shows us several possible improvements to the architecture that we were initially proposing. The first is the database replication can eliminate issues of the single point of failure. The trade-off would be some data consistency concerns and greater complexity. More interestingly, it highlights tight coupling between the scoring process and the audit service. Having assessment scores in a dedicated database would eliminate some of this complexity. It would also add, eliminate some of the coupling, but it would add some complexity. Okay, let's move on to scenario 3. This is attempts to access unauthorized data. Downstream validation and logging improve security and traceability, but they add some overhead. The next scenario is getting those assessment logs under normal conditions. Audit services can bottleneck retrieval. Using a separate database helps contain the impact. The 5th scenario is the high load scenario. Single host deployment limits scaling. And the synchronous service chain amplifies load on the audit service. However, stateless services would scale well under Kubernetes. So right now we're deploying to one server with Docker in our example, but that's not necessarily what we would have to do. We could use a system like Kubernetes. And then finally, the 6th scenario is that change to the algorithm for scoring. Microservices isolate changes well, but scoring still depends on the audit schema. Some updates ripple across the services, even though separate databases reduce unintended side effects. All right. So those are the tables, and we can get into the demo situation. Now, I'm going to demo the the layered system here. So we're going to log in. This is the login screen, and we're going to do a quick assessment. We got that warning because the password is password123, and Google hates that. So Bob, we're going to guess at some heart rate or some statistics there. So I don't know if I'm making Bob really sick or healthy or what, but we're going to find out here.
His blood pressure's a little off. Hopefully the score reflects that.
All right, so we did get a moderate risk. So here we are. So because we're logged in as an admin, we have the assessment search here, and we can go ahead and take a look at the assessment search. Here's the one assessment that we've done, and we can open it up and take a look at the records. Now, we're going to show you the real meat and potatoes here. This is Israel. He's going to demonstrate the microservice system. And I've probably stolen some of your thunder. I'm sorry.
That's okay, Aaron. Thank you. And this is what our microservices would be. Well, let me log out. I'm going to log in as the admin. Same thing. Apple also doesn't like the password, but who cares? Just make a name.
Password 123. What could be wrong with that?
A hacker's dream.
I also don't know medical terms, so whatever I'm putting, hopefully he's alive. Oh.
The interfaces look the same because we were able to use the same web interface for both systems, or very similar ones at least.
This is what the Triage nurse would input from the patient, and it would generate a result. Yikes! Yeah, he's in critical condition.
Izzy's going straight to the ICU.
Or the morgue.
And then the admin could also look at the Triage nurse results from our system, and basically same thing with the layered architecture. We also get our values here showing, where the pain location is and all the important information that the triad admin or nurse would need. Yeah. And then you can log out.
This concludes our project presentation and demonstration. Thank you for your time, and we look forward to seeing what grade we get. Thanks.
Thank you.
Bye.